My name is Brandon Davies from TRC, and over the next 4 classes, I'm going to be presenting on transmission line protection. Once we wrap that up, I'll be doing one additional class on bus protection. So today we're going to cover a variety of topics, but really focus on the basics of transmission lines. We'll take a look at the transmission line and how it fits into the overall power system, what it's used for, some of the physical characteristics, as well as the electrical characteristics. How do we electrically look at a transmission line's parameters, and how do we fit that into modeling? We'll take a look at some fault considerations. What happens to your transmission line and the surrounding system when you have a fault. We'll do an overview of protection system objectives, as well as transmission line protection fundamentals. So to start out, I'll do a little bit of an overview of myself and my career path, kind of how, what I do here at TRC and have done over the years. So we'll start with education. I graduated in 2006 from the University of Maine EET program, and then followed up with a master's degree online covered by TRC's tuition reimbursement program at Michigan Technological University in 2012. In between those two, I did also get my Maine professional engineering license, and I still maintain that license today. As far as work experience, after graduating University of Maine, I started in at TRC and came in as a protection and control engineer. My duties initially, early in my career, were more focused on the drawing, design aspects of our work, working through design packages to support protection and control installations at substations for utility customers. Sometime into that initial role, there was a split within our group to kind of break between folks focusing primarily on the drawing aspects of the work and relay settings, and I went into that latter category. Eventually moved into a supervisory role for that group, and then took a number of progressive leadership positions from there until over the last few years I was the director of our system protection and automation engineering staff of about 60 engineers nationwide for TRC. Last year I took a new position as Chief Technical Officer for the overall substation engineering practice, where I oversee and provide technical expertise and guidance for our overall staff of between 350 and 400 engineers across the country and in Canada. And that's what I'm currently doing as part of my role here. A few other things about my career items. I do have a lot of involvement with the IEEE, specifically the PES Power System Relay and Control Committee. I'm currently a member of the K subcommittee and active vice chair of that subcommittee. That group oversees substation protection standards for the IEEE. It's a volunteer organization, and we maintain and update the standards as new changes come into the industry. Currently a senior member of the IEEE as well, and have gotten a lot out of the involvement in IEEE overall. So a little bit about TRC. TRC is a national and growing, somewhat international consulting company. We've got office locations around the U.S. as well as a few international offices as well. We've got about 7,000 employees that roll up to the overall organization, and we're broken into several different sectors with different focuses. I work for the power sector, which does basically every kind of engineering service that utility, generation client, municipal or co-op or renewables developer could be looking for. Within the power sector, we're split into a number of discipline-specific practices based on the type of work we do. So things like transmission line engineering, distribution engineering, substation engineering, power system studies. Renewable team is a new and growing team. And we're doing a ton of work for utilities really across the country and starting to branch out outside the U.S. as well. So the first thing we want to take a look at when we're talking about transmission protection is what is a transmission line? How does it fit into the overall power system? So generally when we're talking about a transmission line, we're talking about a three-phase AC type of line. There are DC lines, and there's probably some other configurations that are used, but generally, the majority of the power transmission in the transmission system are three-phase AC circuits. Utilities vary in what they define as a transmission line versus sub-transmission, but in general, if you're looking at something between about 69 kV and up to 765 kV, when you're looking at that's generally considered part of the transmission system. Some utilities may use 69 kV in more of a sub-transmission capacity, but it really varies from utility to utility what they consider transmission versus sub-transmission. And really, when it comes to protecting those lines, there's not a lot of difference in how we go about protecting a transmission line versus a sub-transmission line. Maybe other than the amount of protection and the redundancy applied. So a lot of the types of things we're going to be talking about would apply both to a transmission or a sub-transmission line. When we're talking about the transmission system, there's some other terms we use to describe the system and system components and kind of categorize them. And one of them is the term bulk electric system, or BES, and that's a term defined to identify what parts of the system have to meet certain regulatory requirements. And that's generally anything over 100 kV and above. You may also hear the term bulk power system. And that's a little bit more complicated term to define because it's not really just based on a voltage cutoff, but is another term that's used that describes basically the most critical portions of the system used for large power transfers throughout the power system. Your transmission lines can either be overhead or underground. I'd say the vast majority of transmission is overhead, primarily due to the increased cost of underground work and the sheer distances that these systems and lines need to cover. The boundaries of a transmission line are generally terminated at breakers or other switching equipment at power substations or switching stations. So you'll have the line itself that may go through some tap stations and things like that, but generally when we're talking about a line, we're talking about a component that can be switched on and off using the power circuit breakers at a substation. That really defines the boundaries of what we consider a line, because that's really functionally within the system a component that you can interact with. So the primary function of transmission lines is to transmit power between substations or between generating facilities and utility substations. This is a little bit different than a distribution system that is directly feeding customers, and really is there to transmit power from one region to another, or one area to another, as generation and customer loads may not be right in the same area. So this is shown on the very simplified picture here, where we've got a bunch of generation off to the left side of the picture, and that generation is producing the power. It's transmitted through the transmission system up through a substation on the generating side. Steps down through a substation on the distribution side, and then goes out to feed your radial customers. So this is residential customers, businesses, basically things that are consumers of the power being fed. We also have a tap off this line coming down to industrial users. So the transmission system does sometimes directly feed large industrial loads, but generally that's kind of a unique case, and more often we're really using the transmission system to allow us to move the power from our generation down through a bunch of substations and into the customer connections. So obviously that last figure is a very oversimplified version of the power system. It's not a single transmission line connecting from a generating facility into a substation that steps it down for distribution out to customer loads. The actual power system is much more complicated than that. Generally, we've got multiple transmission lines running in parallel. It's a very network connected system that we've got multiple paths for power to flow. We've got generation connecting in at multiple points. We've got loads tapped off at other different points. And it gets very complicated to kind of boil it down to something as simple as the previous picture. So what I've got up on the screen here is just a very zoomed out screenshot of a portion of the power system as modeled in Aspen One-Liner. And you can see in here we've got a number of kind of color-coded lines and kind of a lot of illegible stuff on the picture here. But basically we can boil this down to a lot of these small vertical lines here are substations, and the color-coded lines are lines of various transmission and sub-transmission levels, with the kind of magenta pink colored lines here representing a 345 kV system, the red lines representing a 115 kV system, and then the blue lines representing our sub-transmission system. So as you can see, the actual power system is very complicated, has a lot of components and a lot of options for how we're transmitting that power, and each individual line is a component of that. As you add or remove lines, you're changing the overall electrical characteristics and the way the system will operate. So as protection engineers, one of the first things we really need to understand when we're applying protection is the equipment that we're protecting itself. So if we take a look at a transmission line, we really want to understand the main components and parts of the transmission line so we can make sure we're providing adequate protection to anticipated failure modes and for the equipment itself. So when you look at a transmission line, the main thing that we can start looking at is the conductor itself. So it's a three-phase system, so generally we've got three-phase conductors, and then we'll have some ground conductors as well that'll act as our grounding path and be another part of our system. When off to the right here, I've shown a couple pictures of typical types of conductor. So the top one is an aluminum conductor, steel reinforced, ASCR, And you can see it's got aluminum strands wrapping around the outside of the conductor, and on the inside you've got some steel strands that provide strength for the conductor. So generally, the majority of your power transfer is happening in the aluminum, and the steel is there to reinforce and provide strength to the conductor itself. On the bottom picture here, we have another type of conductor that's commonly applied. We see this used a lot, and that's an optical ground wire. So the optical ground wire is used as a ground conductor for the transmission line, and similarly, it has a conductors wrapped around the outside to be the current carrying path. But then on the inside, it has a reinforced fiber optic cable that can carry multiple pairs of fiber optic conductors to allow communications between the substations and other uses of a kind of system-wide fiber network. So the conductors themselves have to be held up. So we've got in addition to the conductors, we've got the transmission structure, which is a main component of the transmission line, and the structure itself are designed by the civil engineers and other transmission line engineering folks to support the conductors, and there's a lot that goes into that because of the weight and stresses that go in with supporting these large and heavy conductors over long spans. And the transmission structures connect to the conductors through insulators. So your transmission structure would be grounded. Conductors are live, so you need to have something separating those two components, and we use strings of insulators based on the voltage level, determines how many insulators are needed and what the requirements are for those. And there's some other components that go into this. Obviously, there's a lot of connectors and things like that would go into the detailed design of a transmission line, but these are the main pieces that we can kind of think about as a protection engineer. As I mentioned, the engineering that goes into developing a transmission line design includes a lot of different considerations, such as the loading capabilities, how much load, how much power do we need to put through the line, what is the conductor spacing, how far apart do the conductors need to be to maintain electrical clearances, the conductor sag, so that, and that's variable based on temperature and other conditions. The tension of the conductor, there's putting a lot of stress on that transmission structure. The clearances between the line conductors and the ground, between that and adjacent, trees and other vegetation, or between that and other adjacent transmission lines or lines that may be crossing underneath the transmission line. And then finally, wind and ice loading. These need to be designed in a way that they are able to withstand expected weather conditions and other situations that they'd be expected to see. So generally, there's some margin built into any of this to make sure that these lines are able to withstand kind of worst case expected weather events and things like that. So on this next slide, I've got a few examples of what those transmission structures may look like. We've got a few different varieties here with each having their own use cases, and every client will have its own standard on what type of structures to use in what scenario, and that's largely based on the voltage level, the conditions and terrain that you're trying to cross, how far apart your structures are spaced, and just the utility zone preference and uh, and standards. So you can see each one of these has all of the same components here. You can see each represents a three-phase system. This first one, we're calling it section C, is a 115 kV line. Actually, all three are 115 kV lines. And we've got a conductor shown here, and it's the aluminum conductor, steel reinforced with 26 strands of aluminum and 7 strands of steel. The conductor type defines the both physical and electrical parameters of the conductor itself. The static or ground wire up here would be these two conductors on top that are those ground conductors that are separate from the phase but are used to provide a ground path for the transmission line. So we've got the structure itself, we've got the insulators supported from the structure, and then the conductors would hang directly from the bottom of these insulators and span between this and the adjacent structures. Another variety shown here is a single pole. It's holding the same type of conductor and static line. And you can see it's got a different type of insulators that are designed to mount horizontally to support those conductors. And then lastly here we've got a double circuit type tower. So this type of structure would be designed to hold two separate transmission lines because you've got 6 points here you can connect. So you could have phase 1, 2, and 3, and then another line on this side, or they can be spread out between the different points here based on the design considerations. But they all have basically the same types of same types of parameters on here that we're looking at, the conductor types, the static wire types, and spacing and things like that. And that's really what goes into how we take the physical parameters and transition those into electrical parameters. So when we start to look at the electrical quantities for a transmission line, it's not quite as easy as just looking at the conductors themselves and looking at the impedance per foot and multiplying that over the distance of the line, because there's a lot of other effects going on when you're working with high voltages and large power flows. So certainly the conductor itself, the self-impedance of the conductor is an important parameter. The conductors, this 795 kcm ACSR conductor that I have shown up here, has a spec sheet that tells what the conductor's resistance are and other electrical parameters, and that's a big piece of what we use to model the line. Some of the other stuff that comes into play, though, is there's actually some inductance between the conductors and the static wires that needs to be modeled and understood, because we've got a flux linkage between these two conductors that are energized at different potentials or different angles, phase angles of the same magnitude. And they're both carrying current through the system. So there's an amount of coupling that happens between the conductors on the three-phase system. We also have some capacitance effects as well. So we've got some capacitance between the conductors themselves, because again they're at different potential levels, and then we've got capacitance between the conductors and ground as well. That we have to consider. The other consideration is mutual coupling between adjacent transmission lines. So oftentimes you'll see a transmission right of way, and that's one of the clear cuts through to provide a path for the transmission line to be built. Once you've built one of those and cleared out for the right of way, it makes sense to use that for more than one line if you've got similar paths for portions of your transmission system. So oftentimes you'll see that you'll have multiple transmission lines and transmission structures, possibly at different voltage levels, using the same path, and that you know the mutual coupling effect is basically that same idea of the flux linkage between the two adjacent transmission lines, coupling between them. So especially when you have high magnitudes such as fault currents, you do end up with a coupling of current flowing on one transmission line or one phase of the transmission line, also being coupled and showing up and impacting the current and on the parallel lines or adjacent lines. So you can go in and you can take all of those types of parameters, all of the physical spacing parameters of how far apart the conductors are, the electrical parameters of the conductors themselves, information about how high off the ground it is, considering worst case sag and things like that. And you can go in and do hand calculations to come up with an equivalent electrical model of that transmission line. And it would typically be, the output would be something of impedance per unit length, so impedance per mile or per 1,000 feet or something like that, that you can then use to generate an electrical model of the transmission line. We've got a lot of software available that makes it so you don't have to do that by hand. You can go through and run the math and do it. We've got a bunch of engineering tools we use that will do some of that modeling for us based on that same input information, the electrical characteristics of the conductors, the locations and spacing and sag and height of the conductors, and it'll generate a electrical model of the transmission line. So there's a bunch of different ways you can model a transmission line with varying degrees of complexity. But generally, as protection engineers, the way we're looking at a transmission line is we can really boil it down to a fairly simplified model. We don't need a lot of dynamic and transient impacts of what's going on. So we're able to use a fairly simple transmission line model, and what we use is called a pi equivalent model. So I've got an electrical figure here of how we would model a transmission line, and you can see it's taking those parameters that we'd get out of that modeling software, that we've got a resistance and an inductance associated with the conductors, and that's again based on the mutual impacts between the conductors themselves, as well as the resistance parameters for the conductor based on the spec sheet. And then we've got the capacitance of the line, and in reality this capacitance is distributed across the entire length of the line, but to simplify things as far as our calculations and simulations go, what we do is we take half of the capacitance and we put it at each end of the line. So here we've got 1/2 of the susceptance value shown on one end, so this would be one line terminal, and the other half shown on the other end. For most of the work we do, on almost every protection application that we do, we can simplify it further, and in that we really don't use the line capacitance for most of our analysis and calculations. It really comes into play in a couple specific types of protection applications where the line charging capacitance and current is a consideration in selection of the set point. Because basically, when you energize the line, even if you don't have any load current flowing through the line, just the act of energizing it will draw some current from your terminal, and that's because of the capacitive effect here. And you'll see some current, even if the line isn't closed, and that's just the current required to energize the distributed capacitance in the line. And in most applications, that current is so small that that it doesn't cause a sensitivity issue with your protection, but in a couple instances that is something that's important to know. So generally, when we model lines, we try to model that even if it's something we're not using. That way, if we do choose to apply one of those types of schemes, we've got the information that we need to adequately model that. So if we take that transmission line pi equivalent model and want to use it to do some actual analysis, we need to fit that into the rest of the system model. As I showed on the previous slides, a few slides prior, the actual model of the system is very complex. But in many cases, we can kind of boil it down to a very simplified model like what I've got shown up here, where I've got the line impedance, ZL, and this would be the resistance and inductance of the line with or without the shunt capacitive effects, with a system equivalent, Thevenin equivalent, on either end of the line, and that would represent the contributions to the line from the rest of the system. And really, we can boil it down to this type of model for a lot of the analysis we're going to be talking about. And we'll come back to a model that looks like this when we go to talk about some of our specific transmission protection and fault analysis methods. We've covered a little bit about the transmission line physical and electrical parameters. We'll take a look at faults and what we can expect as protection engineers on faults in the transmission system. Transmission lines in general are, I'd say, more susceptible to faults than some of our other transmission system components at substations. And that's really because of a couple different things. Probably the main one is just the sheer size of transmission lines. These could span hundreds of miles, which just gives them a lot of opportunity for failure modes. You've got a lot of equipment there. You're covering a lot of geographic area that can be exposed to a lot of different weather conditions and things like that. Secondly, is there, that across that area, it's less controlled environment than within the substation fence. At an electrical substation, we're able to engineer a lot of things to limit the amount of failure modes of the equipment within that fence. We put down crushed rock and things to prevent vegetation from growing. We may put provisions in to avoid animal intrusion of the equipment to prevent faults from that. We put in lightning masts and things like that to shield the substation equipment from the impacts of lightning, or at least try to mitigate that to the extent possible. And a lot of those things aren't really possible on the transmission line just because of the sheer size of it. So there's a lot of different causes for transmission line faults, and I've listed a number of them here. Really lightning is a big one. These are large, tall electrical structures with current-carrying conductors and paths to ground. That makes lightning a fairly common occurrence on the transmission system. Wind can also be another factor. One of the considerations that goes into the transmission line design is wind loading. Make sure that if the wind is blowing, maybe irregularly, the conductors aren't swinging back and forth in a way they can make contact with the structures or the other phases or other conductors or other things. Ice is another one. Obviously, ice accumulation on a transmission conductor adds weight, and it adds certain stresses to the system that could cause failures. Fire. So if you have a fire, a forced fire, something like that underneath your transmission line, that can increase the likelihood of a fault because of that. Failed insulators is another one. You've got these insulators that are designed to separate your portions of your system that are on different potentials, so your transmission structures and the conductors themselves. And those degrade over time, and may eventually fail. And a failed insulator would be a path for current to flow, causing a fault. I listed animal contact here. It's probably less of a concern at the transmission voltage level, just because the large spacing between conductors and the larger spacing between all of the equipment. But especially at sub-transmission and below type levels, animal contact can be a bigger concern. And finally, physical contact. You may have trees and branches, a vehicle hitting a pole. You might have other physical things that come in contact with your conductors or between your conductors and other system components. And the physical contact piece is something that largely utilities do a lot of work to try to control. There's vegetation management programs that look at all their right-of-ways and make sure that trees are not starting to grow up underneath your transmission lines. Generally, your transmission structures aren't running along the roadside. They may cross the road, but generally they're not following the road like a distribution line would. And they've got some standards and things like that they go into to make sure that these type of preventable physical contacts can be limited to the extent possible. The other thing we'll look at when we're talking about transmission line faults is the types of faults. So obviously we've got all these different causes for the faults, but the faults aren't all going to be the same. You can have electrically different kinds of faults. They'll have different electrical parameters and impacts to the system. So a three-phase fault is a fault between all three of your phase conductors. So this would be a short across all three. These are I guess fairly rare on a transmission line, just because of the spacing of the conductors and things like that. But they do happen. We also have a single phase to ground fault, which is probably the most common, and that's when a single phase of your three-phase system makes contact with ground, and that could be the actual ground, it could be your grounding conductors, it could be the transmission structure, but that's by far the most common because it's a failure of a single system. You can also have a phase-to-phase fault or phase-to-phase to ground fault, where either the two phases have made contact with each other, or the two phases have made contact with each other and ground. The last thing I'll mention is there is a tendency for faults, if they're not cleared quickly, can evolve from one type of fault to another type of fault. So your fault that starts out as a single phase to ground fault may eventually arc over to another phase, to a phase to ground fault, or even to both phases to a three-phase fault. So as protection engineers, we have to not only plan for a single type of fault, but we also have to plan for the possibility that what starts out as one type of fault may turn into something else if it's not cleared fast enough. So if we go back to that electrical model of the transmission line impedance ZL with a system equivalent on either side, we can start thinking a little bit about, how does the power system respond to a fault on the transmission line? And there's a lot of stuff we have to think about on the transmission protection applications, because there's a lot of factors that impact the fault response, the voltages and currents we're going to be seeing at our relay locations. One of the major ones is that, where transmission lines are physically so long and have a distributed impedance from one end to the other, you're going to get a different fault response, a different voltage and current at your relay location for a close-in fault versus a line-end fault versus a fault somewhere in the middle of the line. So those are all situations that we need to cover in our protection, and we have to understand how the system's going to respond. One of the other main things we have to consider is the system's configuration and source strength. So the Thevenin equivalent on either side of the line is going to be impacted by the state of the system that it's representing. So if you have line outages or transformer outages, generation that's turned off or not being used at a certain time, that's all going to impact the source strength, the system strength, the Thevenin equivalent of that system that we use in modeling the line. So you're going to get a different fault response for the same type of fault if you have, the full strength system with everything online is going to be different than if you have outages and equipment that has been removed from the system. And then, as we saw, we also have evolving faults that we need to kind of think about how our protection systems are going to respond to those and kind of understand how that happens. One of the other considerations is, how long that fault is going to last. There's certain failure modes that are transient in nature, something like a lightning strike. Lightning may strike the transmission line, cause the line to trip off, but once the line is cleared and the fault has been cleared by the protection, lightning is gone, so the failure mode has been removed, and you can bring the system back online right away. That compared to something like an insulator failure, that the equipment has failed. Once you trip the line off for that reason, if you close it back in, that failure is still there unless you've sent a crew out to identify the failure and replace the faulty equipment. So we need to kind of think of all that stuff, and one of the challenges is that there's not really a electrical quantity that tells us if it's a permanent or transient fault. So we rely on systems like automatic reclosing that will close the line back in after a fault to try to re-energize it automatically, and if it fails to do so and it doesn't, it trips off again, we lock out the line and send a crew out to investigate what's going on before trying to re-energize again. So we've got some different ways we can go about handling that more operationally than by how we're actually capturing the presence of a fault through the measurement of voltages and currents at the station. So from there we can start to step back and ask some questions about what we expect to see for relay measurements when there's a fault. So for the simplified system here, basically we'd have a line relay, transmission line relay at each end of the line, and it'd be monitoring three-phase voltage and three-phase currents typically. So from that, we've got measurements of phase current, phase voltages. From there, we can calculate our sequence currents and sequence voltages if we want to monitor zero sequence or negative sequence, positive sequence independently. We can also calculate the impedance that the relay is seeing, the apparent impedance at the relay location. And all of those are both magnitude and angles in relation to one another. So uh, when you have a fault on the line, if we take a look at one of the relays, we can start to think about, what is that relay seeing in a normal load scenario versus a fault scenario. So under normal load conditions, we're going to have, you know, near nominal, fairly balanced three-phase voltages, and we're going to have fairly balanced three-phase currents that will be, primarily resistive, with a little bit of inductance in there, but generally they're more resistive than inductive. And the magnitudes of those currents are going to be, fairly low compared to the fault currents. So when you get a fault on the line, a few things happen to those measurements. First is your current's going to increase on your faulted phases. So instead of just being a normal power flow equation, now we've got a short circuit that is putting the system equivalent across a very small impedance. So the current's going to go up on those faulted phases, and the voltage is going to decrease on the faulted phases. For certain types of faults, you can also see, the unfaulted phases having the opposite effect. You may have an increase in phase voltage on an unfaulted phase. You may see a decrease in current on the unfaulted phase as well. And then, the apparent impedance that the relay is calculating is going to change as well. So we're going to have a couple different changes we'll see there. One is the magnitude is going to decrease. So the magnitude of the measured impedance is going to go from something equivalent to the load current to something equivalent to this much higher fault current. And the angle is going to move as well. So it's going to move from a typical load region, which is generally a phase angle in the plus or minus 30 degrees off the resistive axis. And that's going to shift from there to something closer to the line impedance, which is going to be mostly inductive. It's going to be something in the maybe 70 to 80 degree range. So those are some good indicators that the relay can use to tell the difference between a fault condition and a non-fault condition. As I mentioned on the previous slide, there's some things that are going to impact these measurements as well. So one of the questions we can ask is how does system outages impact relay measurements? So if you think of a line outage behind the relay terminal, we're going to basically be removing a parallel path for current to flow. And in doing so, we're going to increase the source impedance. So for instance, this ZS, if that side of the system, we take one of the lines out that's feeding the bus, and that line is taken out of service by removing, opening the breakers for maintenance or some other purpose, or maybe there's another fault that has tripped that line off. There's a lot of reasons you could have that outage, but basically by removing that parallel path, the overall ZS magnitude of that source impedance increases, and because of that increased impedance, the impacts of the current increases and voltage decreases on the faulted phases is going to change. So you're going to get, generally, for taking an outage and increasing that source strength, or I'm sorry, source impedance, you're generally going to get a decrease in the fault current seen by the relay, and maybe a slight increase in the voltage seen by the relay, because more of the source voltage is dropping off the fault impedance rather than the source impedance. So typically when we're running faults, especially if we're looking for something that we're looking for a minimum quantity, we're going to find the lowest amount of fault current for a given scenario as part of our fault calculations. We're going to be evaluating with both all line ins all lines in, and single outage considerations. The other thing that really has a big impact on the fault magnitudes and the measurement quantities is going to be the fault location. So this ZL could represent a 50 to 100 or more mile long line, and you could have a fault that's right outside the station at a couple hundred feet or even less outside of the protection zone, or it could be in the middle of the line all the way at the end of the line. So basically what that does is it's going to impact the impedance the relay sees between it and the fault. So if you have a fault at 50, a three-phase fault at 50% of the line, the impedance between the relay and the fault is going to be half of that ZL quantity. If it's at 90% of the way down the line, it's 90% of ZL. And as you increase or decrease that fault, the impedance between the relay and the fault, the current contribution through the relay is going to change as well. So as for closer in faults, generally you're going to see higher fault magnitudes because you've got less line impedance between the source voltage and the fault. And for faults that are further away, you're gonna see a lower magnitude of relay current measured. And again, this is another thing that as protection engineers, we need to make sure we're protecting the entirety of the line, and we want our protection to be work properly for any of those possible locations, any of the outage considerations, and any other considerations we have for how you may be operating this line. So we've got a lot of things we have to consider when we're selecting and applying line protection. We've got a lot of different fault types, fault locations. We've got different system strength and outage considerations that need to be taken into account. So how do we evaluate all this and make sure that our protection covers all the cases and we're looking at the right things? Well, you can certainly go through and manually hand calculate the fault results and determine what the currents and voltages on the system and at a relay location are for a given fault condition. But generally, we're really leveraging some kind of simulation tool. I've got a screenshot from Aspen up here. It allows you to go through and simulate multiple faults, for different locations throughout the line, or past the line to verify that relays are operating as desired. So we'll really use this a lot as a protection engineer to gain a better understanding of the difference between those normal load current, normal operating scenarios and fault scenarios. Make sure we understand what the limits of the fault cases that we're trying to cover are. The last topic for today is really just to start to scratch the surface on some of the basics of transmission line protection. And we're going to start by taking a look at relays in general and how those are applied to transmission lines. So as I mentioned before, line relaying is typically located at each end of the line at the substation. And you've got a line relay that protects the line from either end or from multiple terminals if it's a multi-terminal line. Modern line relays are generally microprocessor-based relays like the Schweitzer or other relay manufacturers provide, and they consist of multiple protective elements within a single box. Historically, some of the older vintages of electromechanical relays, you'd buy a relay that would provide a single function, maybe even just protect a single phase of a three-phase system. So you had to buy many relays to make up a relay scheme. Today, it's pretty much universal that all new relays are multifunction, and you can do many different types of schemes with the same type of relay by applying elements specific to a scheme and logic to combine those elements to the overall functionality that's desired. Each of those elements needs to have their own sensitivity and delay coordinated with other protection to make sure that the relay is operating appropriately for faults within its zone and is coordinated with faults protecting other zones. So the picture I have off to the right here is an excerpt from a Schweitzer 421 relay manual showing some of the functionality that it has for different protection elements. And you can see it offers, a couple dozen different functions, either protection and monitoring functions and things like that. But we wouldn't, as protection engineers, we're generally not applying every single element in a relay. We pick and choose out of that list to suit the application that we're doing. So generally, when we're doing line protection, we're relying on phase and ground distance elements, the 21 that I have highlighted there, as well as directional overcurrent. That's generally directional ground overcurrent protection. And we'd have multiple levels and different schemes we'd apply using those. And we'll talk a little bit tomorrow about the reasons why we select those schemes and kind of how those elements are set, and that's kind of some of the stuff we'll be covering over the next couple of days. So we have a lot of things to think about. As we mentioned, there's a lot of different fault locations, fault types, system contingencies, and things like that that'll affect the measurements and quantities of the currents and voltages that the relays will see. And there's other considerations as well that goes into selecting the right line protection scheme. Things like the length of the line, both the physical length and where it's located, what things it might be seeing from weather and things like that will vary regionally, and you'll see some differences in how different utilities protect based on that. But also the electrical length. There's a calculation we do called the source impedance ratio that determines how long electrically the line is based on some limitations of the measurement quantities. If you have a really weak system, the line may behave more like a long line than a short line, even if it's physically short. We've got to take a look at line loading and understand what our worst case load current is and power we're going to transfer across the system using this transmission line. We can understand what the tap loads look like. If you've got a station tapped off the middle, that might impact the decision for what protection you apply and what scheme you choose. Mutual coupling, as I mentioned, can have some impacts where fault current from an adjacent line is coupled onto the line you're protecting. You need to understand how that's going to impact your protection. And you've got to understand what type of equipment you have. So CTs and VTs, breaker clearing times, things like that all come into play. And generally, you're trying to achieve a certain operate speed. There might be a reason for equipment protection or system stability, critical clearing time requirement that you need your protection to operate at a certain level and a certain speed to meet your system objectives. And also your available communication. So some of the schemes we'll discuss later on in a couple classes will be communication-assisted schemes where the relays are provided a communication channel to share information about what they're seeing so that both relays or all relays involved can make a more informed decision. And then finally, what do you need for protection for backup? We apply the protection to protect the line, but does it also need to back up another part of the system in case there's a failure? Do we need redundant systems to protect in the case that there's a relay failure or other equipment failure associated with one system, which is very common on high voltage transmission applications. So some of the protection system objectives that we really want to look at on every protection scheme we apply, but certainly something we're going to talk a lot about in the transmission line protection module, are listed here. So really when you look at any protection problem, you should be able to break them down into these components and consider how changes in one aspect impact others. So the first one we're going to talk about is reliability, and that's the assurance that your protection scheme is going to operate correctly. Now, that can really be broken into two parts. There's dependability, which is the degree of certainty that the relay or system will operate correctly when called upon. And then the opposite of that is security, which is the degree of certainty that the relay will not operate incorrectly when it's not supposed to operate. And even though these are two very similar concepts, both related to the overall reliability, there's trade-offs there because the more sensitive you set your element or the faster you set your element may increase your dependability because you're more likely that it's going to trip when there's a fault. But the more you push those aspects, the more you impact your security because the more dependable you are, the less secure you're going to be. So any of these any decision you make that impacts one, chances are is going to have some amount of an impact on the other. So it's a balancing act between these two facets of reliability that we need to consider in any scheme, but certainly in transmission protection as well. Selectivity refers to maintaining maximum continuity of service with minimum system disconnection. So we're going to try to design a scheme that will trip when there's a line fault, but will not trip when there's a bus fault on the remote bus or the bus behind you or an adjacent line, because we want to remove the smallest portion of the system we can to fix the problem. We don't want to be tripping 3 substations worth of load offline when we could have just tripped a single station or a feeder or something much smaller. So that's going to be one of our main goals. We really try to maintain that continuity of service as much as possible. Another one that comes into play a lot on the transmission line protection is the speed. Ideally, you're going to operate to clear a fault as fast as you can. But the faster you operate to clear a fault, the more you're going to start impacting your security of that. If you're tripping. If you're not waiting long enough to make an informed decision, maybe you will misoperate for something that you're not supposed to. Generally, for transmission line protection, we're looking at clearing most faults in under a few electrical cycles as far as the detection of the fault. And we'd use a mix of instantaneous protection at either end. Communication-assisted schemes are pretty common. That have very small delays associated with them, or at worst case, maybe a half a second delay for a delayed type clearing scheme. So it's still pretty fast, and there's a lot of things we got to consider with that as far as system stability limits and things that come out of studies that say the system has to clear within this type of speed, and that's a much bigger factor when you get into the higher voltage transmission level line protection, or really any transmission level bulk power type protection. And the last two are simplicity and economics. So it's desirable to solve this challenging problem with a design that's as simple as possible, because simple designs are more maintainable, they're more understandable, they're easier to troubleshoot, they're easier to put in service. But simplicity isn't always an easy thing to achieve when you're working on a specifically challenging technical problem. So it's a balancing act again of, do you want to develop a very complex scheme that will cover everything as well as you think you can, or is there a simpler scheme that will still meet the objectives, but maybe have some trade-offs that it doesn't do so and quite as fast or secure or dependable of a solution. And then lastly, economics. Economics comes into play in everything we do. And in general, the cost of the relays, the relay protection installation and studies that go into setting and then maintaining the relays is very small compared to the overall cost of building a transmission line or a substation. So generally, most utilities, especially at the transmission level, though it is a factor, they're generally willing to invest in that as a way of protecting their much more expensive primary equipment assets. So we're going to come back to these concepts throughout the next several days, and we'll probably have this slide on all of the other presentations as a reminder of the things we're trying to think about when we're deciding on a protection application and evaluating a protection application. So we're going to use a variety of elements to achieve those protection objectives, and we're going to combine these into various different types of schemes to make sure that we're covering all those different scenarios we talked about, different fault locations, fault types, system strength considerations, making sure we're getting the operate speed we need. So as the last thing for today, I just wanted to do an overview of the types of elements that we'll typically use for a transmission line protection. So the first concept is distance protection. So distance protection is inherently a impedance-based scheme. You're using both voltages and currents to calculate a parent impedance seen by the relay, and evaluating that to say, is the impedance I'm seeing associated with a fault, which would be typically a lower impedance magnitude and an angle somewhere near the line angle or line impedance angle, or is it a normal operating scenario where it's just load, which would have a higher measured impedance associated with a load current, and typically would be more resistive than inductive as far as the load angle goes. So we're going to split that, in, like a lot of our protection, into two different types. So we're going to be looking really at phase protection and ground protection separately. Phase protection is usually using measured phase quantities or positive sequence quantities, and ground protection is using zero sequence quantities to determine if there's a fault. Phase protection will generally be used for detecting line-to-line faults or three-phase faults, where ground protection will be used to detect ground faults, whether they're single-phase to ground, two-phase to ground, or otherwise. So phase distance, again, we're going to be looking at phase quantities, three-phase, phase-to-phase, and phase-to-phase to ground fault types will be detected. We're going to operate on impedance, and we need voltage and currents to operate the element. And we'll use these either in a step distance scheme, which we'll talk about tomorrow, or a permissive or blocking pilot scheme, which is one of the communication assisted type schemes. The phase distance element is directional, and it has usually separate underreaching and overreaching elements that will be combined to provide a full protection for the line. And we'll talk a little bit more about that in the next couple classes. Ground distance is very similar, except for it operates on zero sequence impedance this time, and it's really designed to respond to single line to ground faults and phase to ground faults. Also requires current and voltage inputs, and will be used in very similar schemes, has directionality, and will have both overreaching and underreaching elements. So where a lot of the requirements for these two are similar, we're able to use the same relay to apply both of these elements. Some of the other protection we might consider applying is directional ground overcurrent protection. This again operates for ground faults, but this time its operate quantity for the element is going to be a zero sequence current. And typically we'd use both current and voltage, so there's some other options, because we need not only the zero sequence current for the fault, but we also need something to compare that to get the directional aspect of it. And commonly in modern relays, we're using a voltage measurement for that, though you can do it with a transformer neutral current or a few other methods, current-based methods that you can use for determining directionality, and we'll talk a little bit more about that in the next couple classes. Directional ground overcurrent protection is applied in a couple different schemes. Usually we would apply a instantaneous and inverse time type element, maybe used as part of a pilot scheme, communication assisted type scheme if needed. We also have a switch on default protection. That's another different type of protection that's really there to cover a very specific use case of the a three-phase fault when you close in a breaker to first energize a line. Looks at the phase current, and that's able to be set pretty sensitive because the element itself is only enabled for a very short period of time upon breaker closing. So it's kind of a unique scheme, really intended to catch the case where after a transmission outage, the station closes in to energize the line, and somebody's forgotten to take the three-phase line grounds off. So it doesn't allow voltage to be build up at the station because the station's effectively grounded once you close that in. So it's a very specific type of scheme to cover that case due to that type of fault happening and not being cleared by local protection in the past. And the last type of scheme we're going to talk about is line differential. Really, the line differential scheme can operate for any type of fault. It's unique in that its operate current actually takes in the sum of all of the currents from every terminal, and it uses a communication channel to share that information, and then calculates to see if the current going into the line on one end is equal to the current out of the line, indicating a normal current flow or a external fault. Or if the currents don't add up, that means that there is a fault on the line because there's a source that's not being monitored. So that's another unique scheme we're seeing applied a lot more frequently now that communications are more accessible. All right, well, to wrap up day one here, we covered transmission lines as part of the power system. We took a look at some of their physical characteristics as well as their electrical characteristics and what tools we use to model the transmission line electrically. We also took a look at some fault considerations, causes of transmission line faults, the types of faults we can expect, and some of the system response to fault and what factors impact those, whether it be fault location or the system outage considerations, and really took a look at the way the system responds to transmission line faults. And lastly, we did a little bit of an overview, just kind of scratching the surface on some of the basics of transmission line protection, and we're going to dive into a lot more detail on that in the next couple sessions here. So the next class we're going to cover step distance schemes, and we're going to talk about how we apply why we apply step distance schemes and how we coordinate those with the rest of the system. Day 3, we're gonna talk about pilot protection, and we'll take a look at some commonly applied pilot schemes and how those are used. Those are communication assisted type schemes. And then on day 4, we're going to cover line differential protection and a summary to kind of close out the transmission line topic. Appreciate everybody joining today to go through the presentation. Hopefully you all got a little bit out of it, and we'll have a lot more to come on this topic in the coming classes. Thanks a lot.